goes. So section 2.5 asks you to understand a little bit about continuity. Now, if you wanted kind of a nice general definition of continuous, a continuous function can be drawn without lifting your pen from the paper. Without lifting your pen from the paper. And that's a pretty, user-friendly definition of continuity. There's much more technical definitions. We'll see some of those, but that's generally what's going on. If you can draw something without lifting your pen from the paper, then it's a continuous function. Now, there's a couple of varieties of functions, a couple of ways that things might not be continuous, and we'll kind of categorize some of the things that aren't continuous. So here we go. And this is the handout that I put in the chat. That's also on D2L. You have what's called a removable discontinuity. So that's this one over here on the left, graph A. And what's going on there is there's this little hole in the graph, and instead of the function being defined at that point, it's defined at some other point away from the rest of the function. So it's removable in the sense that you could plug that hole. If you redefined the function at that point, then it'd be a continuous function. So if I took this point and moved it down to here, then I could fill in that hole and it'd be a nice continuous function. I could draw it without lifting my pen from the paper. So that's a removable discontinuity. What about this one over here? Well, we can't close the gap with just moving one point. There's a jump between one and the next. So this is a jump discontinuity. And finally, there's an infinite discontinuity. You'll see this at functions like y equals 1 over x, or stuff like that, where you have a denominator which is 0. So this is just one example. I mean, the function could go up towards infinity or down towards negative infinity like it does over here. It could do the same thing on both sides. It's still an infinite discontinuity. The function can't be drawn without lifting your pen from the paper. So we'll kind of start in a user-friendly way and take a look at this graph of G. It says state where the function, state the intervals on which G is continuous. Well, G is continuous right here. So it's continuous between negative 4 and 2. Now, I guess I'm going to be kind of user-friendly about this and list those with open-ended parentheses. So for this first example, let's see, negative 4 to negative 2, that's part of where the function is continuous. It's also continuous on another interval right here, negative 2 to positive 2. Now, when you're talking about where a function is continuous, you're going to talk about that in terms of the x-axis. So negative 4 to negative 2, union negative 2 to 2. Where's the next interval? And let me let you take a glimpse at what I wrote down here. I'm just kind of keeping up with the intervals. Negative 4 to negative 2, negative 2 to 2, union. Where else? Where else is it continuous? What will be the next interval?
2 to 4.
Yeah, 2 to 4. So it starts here at 2, goes up to 4. So 2 to 4. And then 4 to 6. So 2 to 4. Union 4 to 6. And finally 6 to 8. And let's just put that in one last little color. So those are the intervals where it's continuous. Now it has some jump discontinuities and an infinite discontinuity in between all these, but there's a lot of intervals where this function is nice and well behaved, nice and smooth. So we're okay with that one. So the final answer on that would look something like this.
Wait, what does U represent?
U means union.
Okay.
Union. ION? ION? No. Union. Yeah, ION. So it's union. It's kind of like an and. Well, I maybe say an or breathe more mathematically. So it's this or this or this. It's continuous in the composite of all of these sections.
Do we not use brackets? Is it only parentheses?
You know, I'm kind of bothered by that. Personally, I use parentheses for these just to be user friendly, but in thinking about it, Webassign probably is going to want you to use a bracket here and a bracket here. So that is because these endpoints are defined with solid dots, that they're probably going to want you to use brackets. So if I was to rewrite this, it'd be -4 to -2 with a bracket on the -4. And then I'd also need a bracket on the 2 for this interval. So that would be 2 to 4. And it'd just be on the 2 part. The function is not continuous at the right-hand ended point of this interval. So giving you a look back here, it'd be -4 to 2, union, -2 to 2, union, bracket 2 to 4, 4 getting the parentheses, and then parentheses the rest of the way, like this. My habit, especially in class, is to just say, just use parentheses on all these. So thanks for the question. I'm pretty sure that Webassign is going to want brackets here and here. Other questions or thoughts on that one? Okay. Well, let's keep going. Let's move down to this next one. It says explain why the function is discontinuous at the given number. So in this case, the given number is at -1, and our function is f of x is 1 over x plus 1. So I'll call this one example B. F of x is 1 over x plus 1. So one thing that you can look at when you're looking at functions is the domain of the function, the values of x that you can put into this function. And there's one glaring function or one glaring value that you can't put in. What's one value of x that just doesn't work well in this function?
-1.
Yeah, -1. Thanks, Cole. So x can't equal -1 because then you'd be divided by 0 and the function is undefined. It's not defined when you divide by 0. So that's our domain. But what actually happens near that point? Well, let's take a look at the graph. And I think I've got that one up on Desmos. So let me just pull over to, let me just go over to Desmos. I'll shut this one off and turn this one on. How about if I make that a 1? There we go. Well, what's going on at -1? You've got a vertical asymptote at -1. My dog Aspen's trying to help you guys out. There you go. So hopefully you can start seeing a correspondence between problems with the domain and things with going wrong in the function. Now, if I wanted to, I could put in a graph of x equals -1, and that's your vertical asymptote. The graph approaches it towards positive infinity when you're approaching from the right, and towards negative infinity when you're approaching from the left. So it's an infinite discontinuity. Let's go back and look at the question. Explain why the function is discontinuous. Well, it's all of these things. F of -1 is undefined. That's a problem. You're not going to have a continuous function if something is undefined. The limit as x approaches -1 of f of x does not exist. Okay, let's try and understand that. And actually it's going to relate to the third one down here in this list. So as x approaches -1, keep in mind we got to look at this point from two different perspectives. So let me put that point on the x-axis, -1, 0. And pardon me for a second. I have a little customer over here who's becoming a little bit too annoying. So remember what happens when you're looking at a limit. You have to look at the limit from the right and the limit from the left. Well, as you approach this point, -1 from the right, what's happening to the function? Where is it going?
Positive infinity.
Positive infinity. Thank you. When you approach that point from the left, where is it going?
Negative.
Negative infinity.
Negative infinity. So thank you again. Now, because those don't meet, or excuse me, because those don't equal, the limit doesn't exist. So really, they're kind of saying the same thing twice here. This limit doesn't exist really means that these two limits are different. So they're not equal. They're not finite, that's true, but they're not equal. So if these two limits don't exist, then this one here, right here, can't exist. Because the limit from the left and the limit from the right have to be the same. So you check all three of those. Yeah, and the last one is just false.
How do you know if it's finite or not?
If it was finite, then you'd reach some point with your graph. So let me see if I can't think of one. In fact, let's just take a look at the next one. So if you're looking at the limit as x approaches 0 of this function, notice that the graph gets close to and actually touches a finite value. It's not going to positive or negative infinity. It's getting to a predictable value, so a finite value. Now, this graph does approach negative infinity and positive infinity, but at a different point, at x equal -2. So let's take a look at that and try and understand some things about that with this example. But did I answer your question? You know, the graph is approaching a finite limit, you'd actually be able to see that on a graph someplace. Explain why the function is discontinuous at the given number a. So here's your function, x squared minus 2x over x squared minus 4, as long as x is not equal to 2. If x equals 2, then we're going to define the function as 1. So if x equals 2, the value of the function is at 1. So let me shut off the, no, actually, I guess I don't need to shut off any examples. So we're good here. And the function at x equal 2 has a value of 1. Let's see where that is. Right here. So, now this function is kind of interesting for a couple reasons. Let's take a look at it. And I'm going to mess with the function a little bit. What I thought was scrap paper is not. So getting down to the last of my scrap paper here. example C, f of x is x squared minus 2x over x squared minus 4. That's for x not equal to 2. And it's 1 if x equals 2. Okay, well, let's turn our attention to this part. X squared minus 2x over x squared minus 4. If you factor the denominator, how does that factor?
X minus 2 and x plus 2.
Awesome, thank you. The numerator also factors as x times x minus 2. This function is undefined at 2 points. What are those 2 points?
-2 and +2.
Thank you. Undefined at x equal 2, x equal -2. But keep in mind that the overall function here actually defines what happens when x equals 2. You say, all right, if x equals 2, then the function is going to be 1. So they kind of filled in a little bit of a gap, but there's still a problem here. Now, it does look like, and it does in fact happen, that these two cancel. You still can't put x equal 2 into here, but other than that 1 point at x equal 2, this function is equivalent to x over x plus 2. You know, like I said, as long as x is not equal to 2. This one is going to have a vertical asymptote where? Where is this one going to have a vertical asymptote? Where's the denominator 0?
-2.
-2. Thanks, Michelle. So if you look back at the graph, yeah, you've got that vertical asymptote at -2. Let's just do it this way. Go on to -2, right there. There's your vertical asymptote. How come I didn't get a vertical asymptote at +2? I mean, keep in mind that the function's undefined at +2, right? If you put in a 2 here, this is undefined.
Is it because you crossed it out?
Yeah, it's because I've got that term in the numerator and denominator, the function's still undefined here, but I'm not going to get a infinite discontinuity. In fact, if you look carefully at the graph, what you'll find is you get a jump discontinuity. Let me see if I can't trace this graph really carefully. And right, come on. Oh, really? There you go. Right at 2, the function is undefined. It jumps. It jumps from where we think it should be all the way up to here, this point, 2 and 1. So it does have a discontinuity. You're not going to see that on Desmos. If you wanted to see that clearly, we could set that up on the graphing calculator so that you can actually see that discontinuity. Is there any interest in doing that on the graphing calculator? All right, cool. We'll just move on then. Let's make sure we've answered the question. It says, explain why the function is discontinuous at the number a. At the number a, or in this case, at a equal 2, the function has a jump discontinuity. So at x equal 2, the function has a jump discontinuity. Beautiful.
Why would this not be a removable discontinuity?
You know, I said jump, but yeah, that should have been removable. That was a removable discontinuity because we can redefine that. So thank you. I appreciate somebody being awake this morning. To be removable. discontinuity. Yeah, it's not a jump discontinuity. In fact, this function has two discontinuities. What happens at the other one? At x equal -2, I mean, they didn't ask this, but what kind of
Infinite.
discontinuity do we have at -2? Go ahead, Jed.
Infinite continuity.
Yeah, at x equal 2, there's an infinite discontinuity. Nice. Let's continue with this next one here. Use the continuity to evaluate the limit. This is really just doing what I suggested that you could do last time. So we'll call this one example D. What's your first thing to try when you're trying to evaluate a limit?
Plug in the limit.
Yeah, plug in the limit. If it works, you're done. And that's cool. So let's take a look at what happens with this one. If you plug in the limit, it's going to be 5 times the square root of 41 minus 5 squared, or in other words, 5 times 41 minus 25 is 16. It should be a 5 here. 5 times 4 is 20. And that's it. Suppose you were a little bit unsure about that and you're like, you know, I don't know. I don't trust that. What are some other ways you could convince yourself that this limit is actually 20 without direct substitution? What are some of the ways you could validate it?
You could graph it.
Yeah, you could graph it.
Use a table.
Graph. Perfect. Thank you, gentlemen. You could graph or use a table. All three of these things should show the same thing, that the limit's going to 20. Well done. Okay. Let's move down to this one right here. I don't think I've shared with you the Desmos link that I've been using, so let me take care of that. Actually, let me shut these off first. And where's this example? Yeah, it's down here. So I'll turn these on. Oh. I wonder why I wasn't updating there. Okay, now I can put this link in the chat. It should open up to roughly what I'm seeing right here. So if you want to kind of follow along with that. The one thing that's really nice about Desmos, one of many things, is that you can move the graph around a little bit. And I want to move this one around. In fact, I think the easiest thing to do might be zoom out. So hit the minus key in the upper right-hand corner of your screen. Zoom out a little bit. Maybe bring this down. And I guess I got to zoom out a little more. All right. There we go. That's might be a little bit trickier for you. So I'm just going to put a link back in the chat, put a different link. So it might make it a little bit easier for you to get the screen that I'm getting. But this refers back to the problem that we were looking at just a second ago. And let me pull that problem up so you can see it and understand what's going on. We want to choose the value of C that makes this a continuous function. So there's your function. So this would be example E. F of x has some constant in it. It's C times x squared plus 2x. If x is less than 5, and x cubed minus cx for x greater than or equal to 5. So both of these functions here, or both parts of this piecewise function, are polynomials. And as such, they're going to be continuous. But where they meet might not be continuous. In fact, based on our little graph here, you can see that these don't touch. Is this a continuous function at x equal 5?
No.
No.
It's not. It's not. But underneath these two functions, you'll see a little slider bar. And what I want you to do is I want you to adjust that slider bar. And notice that they're getting closer to each other. And at some point, they're going to touch. And at that point, you've got a continuous function. So somewhere around here, about 3.8 maybe, it looks like that choice of C makes this a continuous function, right? Now, chances are you're not going to graph things and solve this by graphing on an exam. So what are you going to do? Well, let's go back to the idea that we were working with earlier. That is, the limit at a point means that the limit from the left and the limit from the right have to be equal. So let's look at those things. So if this is going to be continuous, then the big point that we have to worry about is what's happening at 5. So let me take a look at the limit as x approaches 5 from the left of f of x. There, that's better. Now, if I'm approaching 5 from the left, that means I'm less than 5. So this is really the limit as x approaches 5 from the left of c times x squared plus 2x. Can anyone suggest a way that I can evaluate this?
Plug in 5.
Plug in 5, yeah. That's our first line of attack, is to try and plug in the limit, and it works. 5 squared is 25. 2 times 5 is 10. So that's going to equal 25c plus 10. That's the limit from the left. What happens is I take a look at the limit from the right. What's different here in working from the right? If you're working from the right, how do your values of x compare to 5?
It's greater.
They're going to be greater. Thanks, AC. So they're going to be greater. That means you're using this part of the function. So here I'll do x cubed minus c times x. And that limit is going to be 125 minus 5 times c. But if this function is going to be continuous at a particular point, then the limit from the left and the limit from the right have to be equal at that point. So basically, these two things have to be equal in order for the limit to exist at that point. So let's take a look here. That's going to mean 25c plus 10 equals 125 minus 5c. And now it's just a matter of solving. I'll add 5c to both sides. That gives me 30c. I'll subtract 10 from both sides, equals 115. So c equals 115 divided by 30. And we can put that in lowest terms if you want. I don't really care. I don't think Desmos is really, or excuse me, Webassign is really going to care either. Let's just get a numerical value for that. So 3.833 bar. So if you wanted to, you could go back and try that with 3.833. And you should get a pretty good match between those two functions. Let's take a look here. That looks pretty good. So the limit from the left and the limit from the right are equal, and it's equal to the value of the function at that point. So it's continuous at that point.
What is
There's
this?
Go ahead.
What does the C value represent again?
C is the choice that makes the function continuous. So if you have a different value of C, for instance, say C equals 2, notice there's a jump discontinuity in the functions. But for the right choice of C equals 3.83, 33, etc., then you get a nice continuous function. Is that
Thank you.
helping out? Okay.
Yes,
Good.
thank you.
Does the visual help out? Is it nice to be able to hit the slider and see that, oh yeah. Okay. And one of the handouts that I put online was for the intermediate value theorem. And let's discuss that next. So let's see. No, back here. Maybe I can make this a little bit bigger. So the intermediate value theorem applies to continuous functions. And again, those are functions that you can draw without lifting your pen from the paper. And it's important that this assumption is met in order for the theorem to hold. If you have a continuous function and your function at one point of an interval, so we're going to look at the function on, say, the interval a to b. At one point, f of a is here, f of b is here. So the function rises from f of a to f of b and going across the interval. The intermediate value theorem says that there's a value on the x-axis that'll line up with any value between these on the y-axis. So if your function goes from f of a to f of b, then every point in between has what's called a pre-image on the x-axis, a value of x I can put in to get that value of y. Sometimes it might be more than one, like in this case. For this value of n, there's several values of x that lead to a particular value of y. Now this must seem really abstract if this is the first time you've seen something like this. So let me try and give you an idea of where you can use this and how you would use this. So one of the uses of the intermediate value theorem is to show that something has a solution. And in this particular case, we're going to look at e to the x equals 4 minus 3x on the interval 0 to 1. So this would be example F. Just trying to keep things kind of in order. E to the x equals 4 minus 3x on the interval 0 to 1. Now, I'm going to rearrange this function a little bit and call it, and create a new function. I'm going to move everything to the left-hand side. So we'll call it, say, h of x is e to the x minus 4x plus 3x. So I'm moving everything over to the left-hand side. If I did that here with the actual function, it'd be e dx minus 4 plus 3x equals 0. And I'm just taking this part and creating a new function called h of x. But notice these two things are equivalent. This is true exactly when this is true. They mean the same thing. So if this is true, then this is true, or vice versa. So where this equals 0, this is going to be true. So if this were to equal 0, this would be true, and then this would be true. So if I can prove that this point, or excuse me, that there's a value of the function somewhere between 0 and 1 where this is true, then I've solved my problem. So let's take a look at this again on Desmos. I'm going to shut these two graphs off. And where do I have it? Intermediate value theorem. Oh yeah, right here. So I'm just going to start by plotting 2 points for this function h. I'm going to plug in h equals 0 and x equals 0 and x equals 1, the endpoints in my interval. And it's kind of hard to see them there. So you might want to do yourself a favor and hit this little house icon. That's a little bit better. Now, the important thing to see is that this function starts out at -3 and goes up to 1.7 something. Okay, so great, what does that mean? Because it's a continuous valued function, you can't get from here at -3 to here to 1.7 without crossing the x-axis. You have to cross the x-axis someplace. Now, where it happens doesn't matter. What you're seeing here, though, is that the function does cross the x-axis someplace. And that's what the intermediate value theorem guarantees, is that, okay, there's a place where this graph will touch the line y equals 0. And you kind of see it here. What's nice, even nicer about Desmos is that when you click these important points, it'll give you an approximation. So the approximate solution here is 0.677. Wow, even better. Now, I think that's more than the intermediate value theorem is asking of you on this one. We'll take a look back here in just a second. I took this problem directly from your homework so that you'll have a good idea of what to see and say when you look at these. So let's look back here. This equation is equivalent to this function equaling 0. So they use an f of x instead of an h of x like I did. F of x is continuous on the interval 0 to 1. That has to be true. If your function's not continuous, the intermediate value theorem won't hold. So first part is that f of x or f of 0 is less than 0. So basically that's saying that the function is negative. And then f of 1 is greater than 0, so it's positive. So the function goes from negative to positive. That means that 0 is trapped in between. So somewhere in the interval 0 to 1, the graph has to cross the x-axis. So there's a number c in the interval such that f of c equals 0 by the intermediate value theorem. And that's it. You're done with that one. You don't even necessarily have to find that value. You just have to show that the function goes from negative to positive. Or it could go from positive to negative, depending on the function. But if it has a change in sign, then it's crossed the x-axis.
So what do you put for f of 0? Like, what would that equal?
They just want to know that f of 0 is less than 0. So that's what they're getting at here.
Oh, okay.
If you see the inequality here, it's that f of 0 is less than 0. Because the function could also go from positive to negative, and it would still have the same effect. So I would imagine that the choices here are f of 0 or f of 1. And in this case, since f of 0 is negative, that's why it's less than 0. That would be your choice here. F of 1 is positive, so that'd be your choice there. But it could be the other way around with different functions. That help?
Yeah, that helps.
Okay. Now, it does lead to kind of a numerical method that you can study if you take some more math as to how to actually find these points. Now, it's a little bit beyond this class, but you can kind of appreciate maybe what goes on here. You could cut this interval in half. Let's say, let's see, let's just plug in a point like 0 and 0.5, or 0.5 and 0, I should put in 0.5 and 0. And look at the function at one interval or the other one. And if there's a change in sign in one interval, then you know that the function has to have a root in that interval. And then you cut your interval in half again. And you keep on doing that until you get as close as you want to the actual value of the root. So it's called a method of bisection, but that goes a little bit beyond what we need here. Whew. All right. How are we looking with section 2.5 here? Let's do a little bit more in terms of domain, just to remind you a little bit about the domain of a function. There's a couple problems that I think I've already got predefined for us on Desmos. The domain is the values of x you can put into the function, or it's where the function is graphed, and they're kind of one and the same. So shutting this off, all these off. Let me scroll back up. And let's see, which one do I want to start with? We'll start with problem number 26. Something like this. X squared plus 1 over 2x squared minus x minus 1. So look at the domain. And this would make this as example G. So the domain of x squared plus 1 over 2x squared minus x minus 1. And call that, say, f of x. Well, in a function like this, you're going to run into problems where the denominator is 0. So it might help if we factor the denominator. And at this point, I kind of certainly have sympathy for you. I was always horrible at factoring these things until I had to start teaching it. And then I started to learn some tricks. One of the tricks you could use is just use the quadratic formula to figure out whether it's 0. You could graph this and find out where it's 0. In any case, let me help you out with the factorization. It's 2x plus 1 times x minus 1. Now, the numerator doesn't factor, so you're not going to get any cancellation. And even if you did, there'd still be a discontinuity. It'd just be a removable discontinuity as opposed to a infinite discontinuity. But there's no nice cancellation there. So the question is, where can the denominator equal 0? Where does that happen?
1 and negative 1/2.
Good, x equal 1 and x equal negative 1/2. So with those values, we should see vertical asymptotes. Let's take a look back at the graph. X equal 1, X equal -1/2. There's your vertical asymptotes. So no surprise there. The domain of this function is everything but those values. Those are the two values that are going to create problems. So your domain is the set of X such that X is not equal to 1 and X is not equal to -1/2. You could also write it in interval notation. It might be easier for you in interval notation. So if you were to think about the points that we can't use, this one and this one, the resulting interval notation would look like this. It'd be -infinity to -1/2, -1/2 to 1, and 1 to infinity. That might be a little bit more user-friendly than this. This is just kind of a fancy set notation. One last one from this section in terms of where something would be defined, what its domain is. Before I move on from this one, are we okay with example G?
Yes.
Thank you. So for our last example, we'll call this one, say, R of X, which would be e to the sine of X divided by 2 plus cosine of pi times X. Well, we're going to have the same worry on this one that we did with the last one. That is, this could be undefined where the denominator is 0. So does this equal 0? Well, the answer is no. Keep in mind that the cosine function is trapped between what two values? It's trapped between -1 and 1. Cosine never gets bigger than 1 nor less than -1. So it's stuck there. So if you were solving 2 plus cosine of pi x equals 0, you'd be looking for a place where cosine of pi x is -2, and that just doesn't happen. There's no solution. So this function is never undefined. If it's never undefined, its domain doesn't have these gaps in it like this one does. Its domain is going to be everything. -infinity to infinity. Let's see if that holds true when we look at the graph. I'll shut these off and turn this one on. Kind of a funky looking graph. I haven't convinced myself whether or not this graph actually repeats or if it looks like it kind of repeats and it gets close. Not terribly sure. But there's your graph. So notice that the graph is defined everywhere. I mean, I can keep on scrolling out and there's no gaps. It's defined for all values of X. Unlike, say, this one here that's labeled problem 30. That one's going to have some gaps. So definitely going to have some problems in the domain on that one. Comments on section 2.5? We're looking good there?
Yeah.
I just have a quick question.
Yeah, please.
So when it talks about like a equaling something, is that in regard to like the limit and what x is going to?
You mean like, let's see, trying to think of where I remember seeing a in these things. back up here.
Yeah.
So what's going to happen with Webassign is that they're going to randomize your problems so that everybody gets different problems, or that if you screw up on the first one, that you can try a similar one again. And that's the value that changes. So in somebody else's version, A might be -3. And in the denominator, you'd have x plus 3, so that the function would actually be undefined at that particular value of A. So that's what they're doing, is they're allowing themselves to write this in such a way that they can auto-generate similar problems just by changing that value.
Okay. Thank you.
Cool. You're welcome. Anything else?
Could you go back to the notes for a second?
Yeah. By the way, not that it'll really come up ever, but I like to refer to negative infinity to infinity as script R, basically all real numbers. In a face-to-face class, if you're taking written exams, you know, I'd be very happy to see that, and I usually give it like a bonus point. Not sure that you have the occasion here, but you never know. All right, let's close the books on section 2.5.